Right. So I'm talking about a project called DataSHIELD, which some of you I know are aware of, and this is basically a project that's being led by a group that's based in University of Bristol, the Data Knowledge Research Group, which is a transdisciplinary group looking at a whole lot of issues around data, co-led by myself from the epidemiology, stats, informatics side, and by Madeline Murter from the social science governance side. In fact, this group's about to move from the University of Bristol to the University of Newcastle. And what I'm going to talk about in this talk is, first of all, I'm going to say something about DataSHIELD, why we need something like what I'm going to describe as DataSHIELD, what it is, and how it works. And I'm going to distinguish, most of the talk's going to be based around horizontally partitioned data, and I'll explain in a minute what that means. At the end, I may talk about vertically partitioned data, but I'm going to see how the time is, because I think it's more important that we have discussion than that you hear lots and lots of stuff from me. Okay, and the bottom line here is that we all need, or science and inferences in science are very strongly dependent on being able to work with a thing that in informatics is called microdata. In epidemiology, it's typically called individual level data, and in meta-analysis on the biostatistical side is often called individual patient data. So all of these are synonyms for a really important concept, which basically means you're going to work with the actual individual level data as opposed to some form of transformed data that combines information across individuals. And basically, microdata are absolutely fundamental to contemporary science and analysis in all the areas which I interface with regularly, with biomedicine, social and public health science, but also across science more generally. And there are at least three important reasons why you want to be able to work with individual level data if you can. First of all, there are some analyses that you literally cannot do unless you have access to the individual level data. Secondly, there are some settings where if you use the individual level data rather than some transformation, you get increased power, so you get increased efficiency. And thirdly, there's a lot of settings where being able to work with individual level data rather than having to keep summarizing things before you work with them gives you greater flexibility for analysis. So basically, being able to work with the microdata is really important. But, as has just been very nicely illustrated in Ross's presentation, there are a series of important constraints and barriers that effectively hinder our access to the sharing and combining microdata. And the important point that's coming out from what Ross is saying is that these are good reasons why we can't do it. These aren't things that we want to try and get around. These are things that reflect basic principles as expounded by Ross, and therefore we need to work out how we work within a framework where those things do exist, and we're going to work with that framework properly. And in broad terms, there are three sort of broad reasons why it's not easy or appropriate to just be spreading around individual level data. The first one is the topic of what Ross was talking about, so basically ethical, legal or other governance restrictions. And so, for example, if you look at, so the studies that I'm particularly involved in most heavily at the moment are the ALSPAC study, which is a child cohort study that's been running since 1992 in Bristol, and the 1958 birth cohort, which is a national study that's based on a birth cohort that started in 1958 and is currently run by the Centre for Longitudinal Studies under UCL. Now, in both of those, there are clear statements in the consent forms and in the forms and in the other governance documentation that's been through repeated ethics committees that basically put important constraints on what you can and can't do with individual level data. And those, as they stand, are immutable. So basically, if you want to change any of those things, you're going to have to go and seek re-consent. So that's one example. Now, historically, so one of the people that I work most closely with is called Bartha Noppers, who's a health ethics law professor from McGill University, and she did a review about 5 or 6 years ago of the governance documentation of a lot of the world's big biobanks. Now, and until basically if we're talking about up to about 2 decades ago, there were studies that basically literally said when the data was collected, your data will never ever be passed to anybody else outside the group of people who collected it in the first place. And this is becoming quite unusual now, but nevertheless that did exist. So if those sorts of statements exist, then that's how you have to operate. Secondly, much more commonly now, and is still built into some studies, there are regulations that prevent the individual level data being passed to out of the legal jurisdiction in which it starts off in. So for example, from one country to another. So these are key issues that actually prevent the microdata being passed around. Then there's also in practice issues that hinder the passing of the individual level data around, even if in principle you could share them. And for example, so to give you an actual real world example, about 2008, we had major work going on in the 1958 birth cohort to support the Wellcome Trust Case Control Consortium, which is one of the major groups looking at complex disease genetics and doing the first big sets of genome-wide association studies. And basically, it got to the point in 2008 where there were some groups, everything was moving so fast that some groups knew that if they couldn't publish data, get data within the next 6 weeks and then move on to publish it, they would be beaten by their competitors. So that immediately meant that waiting 6 weeks for data, which may be quite reasonable under other circumstances if you go through a governed system, was not going to work for them. So basically these are issues that challenge what's happening. So that's the first broad thing. The second broad area is in fact, so we saw Mark Walpert in the previous talk, and one of the things that he really has pushed nationally and internationally is that basically when people collect individual level or data of any sort on the basis of public funding, then those data should be being made available to other people to use so you can optimize the value of them. Now, in fact, again, as if we talk about this is a complex issue, it's not a simple thing that's got to be the right thing to do. Because, for example, if you've been running a study, let's say some of the more elderly epidemiologists, so some who've been running studies for 50 years in the UK, they've put their life's work into it, they've never been told before that they have to give their data up for sharing. So the question is it appropriate that you require them to give their data up for sharing? And so that's one issue, which is an example. Another issue which in a sense brings the dilemma into really clear is, for example, one of the big things that's been happening in the last 2 or 3 years, in fact the last 5 years really, has been the setting up of biobanks in Africa. So there's been a big project called H3 Africa, jointly funded by Wellcome Trust and NIH. Now, if you're a group working in Africa, you've used a lot of your very limited resources to collect a set of data from your local population. You want to collaborate with people internationally. Do you really want to be forced to physically give up your microdata? Because the point is, once you've given up the microdata and passed it on to someone else, then you lose complete control over what's actually going to happen to that microdata going forward. And the point is that because you're coming from a resource poor region, you have not got access to the resources that allow you to easily leverage on that to do the secondary research that then produces the results. And so you can very rapidly lose a lot of the intellectual property that sits in your data. So the question is, so if you want to have some control over intellectual property, then you need to think about, do I really need to physically pass individual level data around if I want to work with other people? And the third reason why we have it's not good to, or not easy to spread around individual level data is literally a modern issue in terms of the physical size of the data. So in biomedicine at the moment, the really big data sets relate either to omics data, particularly sequence genomics, where you can get objects of terabyte size, and the other one is in images. So medical images are also very large, and you might prefer to have them sitting around. So these are the reasons why it would be nice if we could not have to move and share physically the microdata. Now, so how can we deal with this? And if I basically, unless at some point I manage to get some funding for DataSHIELD development, this may be the approach that I have to take going forward as a rather simpler way to develop privacy protected analysis. But at the moment, I'm still optimistic that I will be able to get that funding. So the DataSHIELD approach is basically to take the analysis to the data, not the data to analysis. So we're not asking people to send their microdata centrally. Rather, we're asking for that microdata to be left on the local servers where it originally sits, behind those firewalls. And then the purpose of the analysis center, when you've got multiple studies that are working together, will be to coordinate parallelized analyses in all those studies simultaneously. And basically, in order to produce this, make this into a joint analysis, we want to tie those analyses together with some form of non-disclosive information. And I'll say a bit more in a second about what that might be. And a key point about the approach that DataSHIELD works is that, first of all of the analytic processing is done remotely at the site where the data is held. So it's the size, for example, it's the power of your local data servers that determines the speed of the analysis. And secondly, there's a series of disclosure control options that I'll say a bit more about. And again, those located with the data and are completely under the control of the person who is responsible for the data, not the person doing the analysis. So that's the underpinning thing about DataSHIELD. And finally, before telling you how DataSHIELD actually works, I just want to make an important distinction between two types of data partitioning. So in situations where you're using DataSHIELD to try and pull data together from multiple sources, those multiple sources could hold data in one of two distinct ways. So under horizontal partitioning, each of the individual studies holds all the variables you need for analysis, but on different individuals. Now this, for people used to working with meta-analysis, this is equivalent to what happens in a meta-analysis setting. Basically, you've got individual studies, each of which is going to do the same analysis because it's got the same variables, but it's on different individuals. And we want to take that information and in some sense pool it to produce a joint analysis. So basically, horizontally partitioned data and its analysis is relevant if you want to do that securely. Is relevant for secure meta-analysis, which could either be study-level meta-analysis, which is the classical thing that generally happens in the medical arena, where you take results, completed results that have been produced from different studies, and pool all those together, and typically do the pooling in a weighted way, which is normally weighted inversely to the variance of your estimates. So study-level analysis is one, but then there's also individual level patient data analysis where you actually work with the individual level data and pull that together most efficiently. And I'm going to illustrate that with what I'm going to show you with DataSHIELD. Then it happens to be that once you've managed to set up a secure way to do either of these two sorts of meta-analysis, then if those security issues are built into some form of parsing or algorithms that are checking what's happening in your system, then there's actually no reason why you can't then apply those to a single study. So basically it's a way of producing a form of some sort of disclosure protection. Vertical partitioning is, there's several people in this room who mainly work with vertically partitioned data, so this is what happens with record linkage. And so in this setting we've got different sources of the data hold different variables on the same individuals. So, for example, Andy Boyd, who's sitting at the back, is basically in charge of record linkage in ALSPAC. So we might want to pull together a series of research variables from ALSPAC with, for example, general practice data from those same individuals. And in that setting, ALSPAC and the general practices have got data on the same individuals, but it's different variables. So basically that's vertically partitioned. What you might want to do here is some sort of secure processing analysis of the linked data without bringing the data together. Now, virtually everything I'm going to talk about today is in fact the horizontally partitioned data. If I get time at the end, then I will quickly mention the vertical partitioning, which in many ways is more interesting from an informatics perspective, but I'll start off with the horizontal partitioning. Okay, so the challenge that was presented in 2009 was presented by a guy called Michael Wolfson, who at that time worked for Statistics Canada. And basically the question he asked was that, given that microdata are analytically critical and yet potentially sensitive and can't easily therefore be passed around necessarily, is there a way that we can ensure that the information driving the analysis that you want to do across multiple sites only ever emerges from behind the firewall of each data source in a non-disclosive form. So basically nothing is going to come out. Do I get a, is there a pointer on here? Oh yeah. So nothing's going to come out from from these data servers sitting here. Nothing's going to come out and go through the firewall unless it is in some sense non-disclosive. And in fact, there are two broad ways that when when information does need to come out, that it could be made non-disclosive. One is encryption, and this is what's actually used for vertical data shield. And I'm going to discriminate with a terminology that I'm sure is totally incorrect, and I'm sure people would criticize and maybe can give you a better idea. But I'm referring to trivial and non-trivial encryption. Trivial encryption is simply the encryption that you would use if you wanted to send anything securely around the internet. So I'm assuming that we're going to use secure protocols for passing information around the internet. But then the non-trivial bit, the bit that gets interesting, is when we deliberately encrypt and then decrypt information in order to allow stepwise analyses to take place in a way that at no point can you tell what the inferences are and what the original data was from that data. So that's encryption, and that's the basis of vertical data of the vertical partitioning analysis. And then the way that the fundamental center of the horizontal data shield is basically to make sure that what you pass out of these is some form of low dimensional statistics, which are ideally what are called sufficient statistics. So they're things that carry all the information that you want about a particular analysis. And a really simple example of this is a lot of studies historically in biomedicine are quite happy, for example, to share the proportion of individuals who have a particular characteristics in a data set. So that is being allowed to be passed out. That's an example of a sufficient statistic, in fact, for the proportion of individuals that have a study, that have a particular variable. So basically, we're used to that sort of thing happening, but as we'll see, there are a lot of other really quite much more useful statistics that we could use that allow us to do a much broader range of types of analysis. So let's see how it works. So this is a study. We've got an analysis computer, say, sitting in Newcastle. We've got 6 data computers, each one sitting at a study, and our aim in this instance is to do a multi-site data shield analysis on horizontally partitioned data. So we want to do effectively a similar analysis in each of these and then combine the overall results in a form that is equivalent to working with individual level meta-analysis. So 2 key points. First of all, we've got this firewall, and we basically, as I've said already, don't want to pass anything out from that behind that firewall that basically says that is the raw data or gives you information about that raw data that you don't want to pass. And secondly, the other point to note is that there are 2 issues about that. One is that we've got a parser that's going to sit somewhere here that's going to mean that the analysis that takes place here is only allowed to use a restricted series of analytic functions. So that is the first part of the way that you protect against disclosive analysis. And then the second thing is that in addition, there are some analyses that you are allowed to do that produce a range of results which sometimes could be a form that would be disclosive, and therefore you want to be able to block those disclosive ones as they come out. So you also need to check what's going back out again. So basically that's the fundamental basis of the structure. And the key point to say here, so this started off multi-site data shield, but in fact those same restrictions that allowing us to have this extra disclosure control in the multi-site could instead be used just on for a single study, giving us a secure data enclave based in this case on freeware, because I'm going to describe to you how this is actually done, and it's all based on open source freeware. Okay, so now let's be a bit more specific. So I'm going to describe there's 3 classes of function that we run within DataSHIELD. The first one are ones that allow one-step analyses. So an example of that is DS table 2D, which is the DataSHIELD function that will fit a 2-dimensional table. And basically this is effectively a one-step analysis, because what happens is the central computer asks each of the individual studies to create its own 2-dimensional table and then pass that centrally. That is fundamentally disclosive, non-disclosive with one rider I'll come to in a second. And once you passed those to the center, then producing the combined table is simply a matter of adding up the values for each cell from all of the tables. So you can produce the overall combined table in that way. Now, the rider on this is that, as you will know, if you apply for census data, for example, and you ask for a contingency table, they're likely to have a rule that says you will not be able to have the table if, for example, one of the cells has below n count in it. And there's a lot of argument about what that n should be. And at the moment, it's increasingly going up to 10. There's a lot of, I have major issues about this from a theoretical perspective, but nevertheless, that's the reality. And so one of the things that we do into our table 2D is we build in a check that basically checks that the cell count in each cell exceeds some value, which can be set by the data custodian right at the start. And any table that then has less than that will basically be blocked on the way out, so it won't be published. All right, so it won't be presented to me. The second type is multi-step analysis. So these are ones, and a good example of this is a thing called DSLexis, and for anybody who's done survival analysis, a Lexis table is a table where if you've got a survival period for someone, which basically involves how long they survived for plus whether or not they died at the end or not, then you basically break that down into blocks, and each block says that they survived for this long without dying, then this long without dying, then this long without dying, and then finally they had for this long, but they did die at the end of that. And that's called a Lexis diagram. And the Lexis function divides simple survival times up into this form to allow us to do certain types of survival analysis we want to do. And the reason why this is multi-step is that in order to do this, in order to combine Lexis information across multiple studies, you've got to have the same time periods that you're going to break it up to in each of the studies. And that's fine for all the ones that you know, but the one you don't know is you don't know how long the longest survival time that you need to have depends on what the longest survival time is in any one study. And so basically what you do is, first of all, you send a request out to each of the 6 studies saying what is the longest survival time of anybody in your study. That then gets passed back, but that in fact would be viewed as potentially disclosive because it's telling you the maximum value of a variable, and that is viewed as a potentially disclosive thing. So in fact what we do is we add some random noise to that, so what gets passed back is greater than the value it actually is, but you don't know how much greater. That all gets passed centrally. This center then works out what the maxima of all those maxima are, and basically that then defines the survival time, all the survival time groups, and then you ask for the Lexis diagram to be created with that. So that's the second type, multi-step analyses. And then the ones that's most interesting are iterative analyses. So this is exemplified by generalized linear modeling, and I'm going to describe over the next few slides how you do that. And critically, one of the things you need to recognize is that the way that I'm going to describe to you for fitting generalized, yeah.
Well, can you explain why would you need to even ask that question about the maximum value if you have a variable where you generally know what the upper bound could be? Like, is this just to try to get everybody into the right ballpark, or?
Well, first of all, you wouldn't necessarily know what that was. I mean, in practice, often you don't need to know that. You could just set a very, very large number. But I mean, in a sense, it's almost trivial. Basically, this is allowing you to have a whole series of time periods that are all the same in every study, and the top one isn't being set to 1,000 years or something. You could do that in this instance. So, I mean, it really isn't very critical as an issue.
Well, I guess it's just a little strange because you do have the noise model that you're using here is one-sided. Right?
But the noise issue is irrelevant, because once you then do the analysis, let's say that the top maximum time in anybody was 17 years, and that happens to get reported back as 19.1. Okay, when you create the Lexis diagram, it simply says in that last survival time up to 19.1, how long did you survive and did you die? And that means that the actual maximum person will only contribute up to 17.2 in that. So it's really a trivial issue of how you do the calculation, rather than it has no meaning at all in the analysis. the data that comes back is exactly the same ultimately. Do you understand what I'm saying?
Yeah, I understand exactly what you're saying. I think we're talking past each other because my question is more about the disclosive nature of a one-sided randomness mechanism.
Oh, sorry. Okay. Well, so look, yeah, that's a different issue. So could we talk about it at the end rather than now? Yeah, because that's something that would interest me to discuss. Yeah. So an important point here is that the way I'm going to describe how DataSHIELD works here is doing the equivalent of an individual level meta-analysis, but in fact it is equally possible to do this as a study level meta-analysis. And just to tell you what a study level meta-analysis would do in this setting, if you wanted, for example, to fit a logistic regression model, what you would do is the central computer would ask each of these studies to fit a logistic regression model right through to convergence. It would take the estimates and standard errors, then it would take the estimates and standard errors of its key parameters and basically combine them with do a weighted mean conditional, weighted on the basis of the inverse variance. So we can do a study level meta-analysis, and then a lot of genomics work is based on that study level meta-analysis approach. Right, but what actually happens for the individual level one is that basically we start off by sending out a command to each of the 6 computers, and what we're doing is fitting a generalized linear model which has got it's a binomial family model, which basically means logistic regression in this case. This defines what the model, and in this case this model is a case control model. We've got a variable measuring the body mass index. We've got a variable that's actually allowing the effect of body mass index to be different in 3 of the studies compared to the other 3, so it's a heterogeneity term. And then we've got a SNP, a single nucleotide polymorphism variant from the genome, which has 3 levels. You've either got no copies of the abnormal SNP, 1 copy, or 2 copies. So that's the basic model as it stands, and we're sending out in addition a starting value for the estimated beta vector, and typically we're going to start with what's typically used, which is a vector of nulls or zeros rather down there. And critically, we're going to tell the GLIM to fit only 1 iteration. So it's going to take this data with this starting position, fit a generalized linear model or a logistic regression model for 1 iteration, and it's going to get, at the end of that, it's going to calculate 2 things, and these now are the sufficient statistics that we're going to calculate. And these are the score vector and the information matrix. So for example, study 5 creates that score vector, that information matrix, and passes them centrally. And the next thing is that those score vectors and information matrices are all going to be added up across all of the studies. So we'll have the sum of the score vectors from all the studies, the sum of the information matrices. And key point about this is if you work with the updating of a generalized linear model using the iteratively weighted least squares algorithm, it happens to turn out that if you take the sum of the score vectors divided by the sum of the information matrices or multiplied by the inverse of the sum of the information matrices, you actually get the update term that allows you to update your beta vector for the next iteration. So if that first update term converts the beta vector from 4 zeros into now this new beta vector, this gets passed out again, and you're asked to fit the next iteration. You fit another iteration, and that then gets passed back. And basically, we keep going through this process until the model converges. And so in this case, we're going to end up with this set of estimates, this set of standard errors from this particular synthesized example. And first of all, what sort of results do we get? And the first thing to say is that if we fitted the same data by doing a central warehousing approach, taken all the data that's underpinning this from all of the 6 studies, putting them all centrally and analyzing them using a standard generalized linear model, then basically we get the answers we get up here. These are the DataSHIELD analysis, and in fact they're actually identical. So these are not similar, these are the same analysis basically. And if you actually follow it through, you can actually see even each iteration is giving the same answers. Now, it's actually very easy to explain why that is. Some people just literally refuse to believe that it's true. So we've got a paper that proves that it's true. It's very simple, but I won't describe it now unless someone wants to ask about it.
Does this hold true regardless of disclosure control applied on the links?
Yeah, because the disclosure control, basically our disclosure controls always prevent any something being returned. So it's not like we modify what comes back. So yes, no, it does. Okay, so let's actually, in a sense, the maths of this is actually fairly straightforward, and the more difficult bit, which was largely down to our collaborators on the informatics side from McGill University. This is the actual practical application or implementation of DataSHIELD. How does it work? So first of all, it's all based around a databasing system called Opal, which is a MongoDB database that can work both SQL and NoSQL. And basically, so at each of these studies, so here we've got 3 studies that happen to be 3 of the studies that we used in our first pilot study. So this is in Finland, this was in the Netherlands, this was in the UK. Their data sits in some form of server that they've got, sits there, and the first thing that they do is they move the data that they want to be allowed available to analyze through DataSHIELD. They move that out into a data table in Opal. So each of the 3 studies have got data sitting in their Opal data table. Now within these Opals, there is an instance of R that's been embedded, and the key point about this is that this is a normal R, but no commands can get into it without going through a parser, and that parser is only going to allow the set of functions that we've allowed it to do, and I'll say a little bit more about that in a second. So that we can only, it will only run permitted analyses. And the way that this is driven is that we have the analysis client sitting here. Typically in our real world implementations, rather than having the analysis client go directly to each of the studies, we typically go through a central place. So in the case of this project, there was a BioShare website sitting in Groningen in the Netherlands. So the this analysis client can be anywhere in the world. They log into the Groningen center, and then the Groningen center sends their commands to the remote servers and takes the results back, and it all comes through here. So these servers never need to accept anything coming in from any IP address apart from coming from the BioShare website. So that's how we basically set it up. The central driver of DataSHIELD are these other special functions we've got. The server-side functions are ones that sit within these R environments that are on the remote servers. So basically, this is the set of functions that are allowed under the parser to actually take place. So basically, there's a set of we've written functions that will only do what we want them to allow to be done. And if you try and do something in that R by calling externally through the Opal, you can only use these special server-side functions. Then on the client, which is a completely normal R environment, just sitting wherever you are, we put client-side functions, and the role of the client-side functions is to communicate with the server-side functions, because it's quite annoyingly complicated to write the server-side functions directly. It also coordinates results when they come back, for example, that working together with the outputs of the score vectors and information matrices from during the GLIM fitting. Okay, and so key point, this is all of this stuff that are, as you all know, plus Opal, these are all open source freeware, so this can be set up very cheaply. At the moment, current research activity focuses around, these are actual scientific studies that are running DataSHIELD at the moment. So the Interconnect project that's led from Cambridge, Spirit that's led from China and from Quebec, Enpadasi, which is a nutrition study in Germany, and then BioShare EU, which is the original study, which is a European Union-based study from Groningen in the Netherlands. And then we're working closely with the FAR Institutes, the UK Data Archive, and some of the work we're looking at the moment is in link with the F1000 Research Journal as producing a potential way to do post-publication presentation of sensitive data. I'm just going to finish then now. So if I finish in the next 5 minutes, then we then have 5 minutes of discussion, don't we? Okay, all right. So these are some important reflections. So first of all, so DataSHIELD is aimed at allowing governance constraints to be met in full, while you can rationally lower the governance bar. So if you can basically put protections on what can and can't be seen and used by a user, so if a user literally cannot see the data, the user cannot copy that data, and there are also some disclosure controls on the information that can come out, then that rationally allows you to think about lowering the difficulty of the governance process. Secondly, it basically provides an effective solution to a range of challenges in data management, but it is not always appropriate. And sometimes people get the impression that we are proposing that every study should be done using DataSHIELD, and absolutely not. That is not what we're proposing at all. It is sometimes inappropriate to use it, and inappropriate settings include situations where the disclosure protections for DataSHIELD are either too weak or unnecessarily rigorous. And if they are unnecessarily rigorous, then it just wastes everybody's time, both in terms of setting the thing up and then in terms of doing the analysis. Ideally, I mean, I personally think it's essentially, but it certainly should be ideally, DataSHIELD should be applied on top of a system of data access and governance that is already well founded. So I would feel nervous about someone taking DataSHIELD, applying it into a study that's basically running as if it was in the Wild West, and then saying, all right, we're protected because of DataSHIELD. DataSHIELD is something you add to a proper system that already exists. And a key element of this is that the Opal servers that hold the data, in my view, should never ever be the same servers that you hold your raw data in. If someone was to use the link into Opal as a way to hack into your system, you really don't want them to be able to hack back to your original data. If you lose your DataSHIELD data, it can be annoying and it can have confidentiality issues, etc. But it's not the same as having someone going in and screwing up your original raw data. There's a major issue of long-term sustainability, so one of the things that we're definitely looking to is developing a cost recovery mechanism, and in fact, in contrast to a lot of other areas I've worked in biomedicine, medical data use, I think that would actually be feasibly possible at a realistic cost. And a key issue about DataSHIELD, one of the main reasons we've developed it, and this is particularly noted by people coming from lower and middle income countries, is that because it allows efficient access to the full information held in sensitive microdata, while those microdata remain with their original generator or formal custodian, it basically can promote trust-based collaboration, so people can feel a lot more confident that they are not going to get screwed by their collaborators, as well as having protection from the ethical legal issues that need to be dealt with. A key warning here is that, and again, this is, people sometimes treat DataSHIELD as a magical thing, that if you take data from 3 studies, put it through DataSHIELD, and you're going to get the right answers. But before you do anything, you've got to clean your data, harmonize it, and realistically, in the real world, that workload is actually a lot harder than the actual work of setting up the DataSHIELD and doing the analysis. So basically, it must never be forgotten that you have to do that. A plea that I have here is that I get really nervous and irritated, in fact, by extensive discussions about whether the nation should be investing in central warehousing, much as Ross talked about earlier on, or whether we should be working with remote federated analysis. It strikes me that both of these approaches are needed in different settings, and I can give examples of the 2 settings where I think that they are appropriate. And a key point about DataSHIELD is that although it is of value, it was developed for the federated analysis, it can also be applied to data that has been centrally warehoused in a really well-founded central repository. And then the final point relates to discussions this morning about differential privacy. So the issue that's referring to, we tend to call inferential disclosure. And basically, it's important to recognize that no matter what you do with DataSHIELD, you are still at the mercy of the fact that if someone does manage to do a series of analyses that do allow an inference to be drawn from the closely allied set of analyses you've done, then you do have the risk of inferential disclosure, and you need to be aware of that in how you work with DataSHIELD. And we're thinking about a number of approaches to that, and the talks this morning actually raised some additional questions that I'd like to explore with people. Okay, thanks, Chris.
Thanks very much. So we do have a few minutes to discussion and questions. Could I perhaps just start?
Okay, yeah. Sorry, do you want to follow up on that, the question you asked? Because in a sense, I'm more throwing the question at you because I'm interested in the answer. So in this particular instance, this is a trivial issue. It's not particularly important, but the issue of that you've mentioned about how useful it is to do one-directional masking of things. I mean, what is the issue that you're?
I don't know. I mean, it really depends on how I would hack the system. I haven't thought about it enough because what you do reveal is the lower bound on these values at that point, and it just depends on if that feature itself can be exploited in any way. I don't know.
Okay.
That's just one concern. I guess I have other questions, which is about. So, do you have side channel problems?
Do you have what? Sorry.
Do you have side channel problems in that are people publishing papers about their data sets before they get involved in this type of an investigation? And if so, what types of statistics are they publishing?
Well, first of all, people could publish stuff. We're not in any sense. We're effectively providing a tool that they can use. And so if they publish stuff and then did it again, then did the work again within DataSHIELD. I mean, is it you're saying, for example, if let's say there were 5 studies that were estimating a particular thing,
well,
4
let's
of them.
play it even simpler.
Okay.
2 studies. So if one person, I mean, like one of the problems that you run into in these types of multi-party computations is that you usually have to have a minimum of at least 3 participants in order to keep a secret.
That's one of the things that we're.
Is that so? But then what happens is that you then have to start asking questions about: do you run the risk of having coalitions or factions? Where, I mean, it's a small community that you're talking about here in terms of who manages this data and who collaborates together. And so you may have a situation in which you might have. It's not uncommon to see teams across 3 or 4 or 5 institutions all doing their first publication together. And they use like a coordinating center. So we do this in the U.S. where you have like an NIH or an NHS sponsored coordinating center that is allowed to have the integrated records to begin with, can provide feedback back to everybody.
Oh, nobody's. When you say do you mean the integrated records including the individual raw data?
Sure.
Well, no, that none of these do that.
But that happens all the time in large trials.
Well, but in that case, my view would be if you've got a group of studies that are prepared for a single institution to hold all of it, then don't use DataSHIELD.
Right, but where I'm going with this next is that that's one study.
Yeah.
So now you want to embellish that study with additional data because you might not have achieved the statistical significance you were interested in. And so, but now you have potential participants in your program that all know what each of these groups would be contributing, right? Because they were part of some coalition beforehand.
So are you saying that they would, because I don't see that would allow them to draw inferences at the end of a level of individuals? Because it's different. That one.
I actually do think of it. I mean, so this is actually some of the work that Nancy Cox's group has done, in showing that based on regression coefficients and certain information that you get off the aggregate statistics, that you can start getting back towards individual records.
Well, I'd have to see that because I don't actually believe that's true in this instance. For example, I know a case where it is true, which is, for example, in genetics. There's a major thing. There was a paper written by Homer et al. In 2008 where they showed precisely that if you were given just the coefficients relating the estimates of each of a whole series of genetic variants in a genome-wide association study, yes, you could do exactly what you're saying, but I don't think these ones would do that.
In 2011 by Heikki, Kamen,
yeah.
and Nancy Cox on use of quantitative trait loci and regression coefficients.
Oh, so again, is that a genetics one though?
Yeah.
No. Okay, if you've got multiple things, say you've got a million things from a SNP thing, then there are a whole lot of stuff you can do. But at the moment, this is not specifically being designed to do genomics, and that's one of the things it can do. But
this could be a fun debate because play this out. Just keep playing it out.
Yeah.
So how do people use the system? So what types of queries can they issue? So they could issue a query for SNP1, then they could issue a query with respect to SNP2.
Yeah.
They could issue a query with respect to SNP1 and SNP2. And so now you start building all sorts of coefficients across.
Yeah, but
models
you've got to get, if you think about it, to get inferences at the level of the individual, you've got to have a total model information size ultimately that's getting close to the total sample size n.
You're still going to have to reveal, for instance, how many people there were that were in the study, right? That knowledge still has to be disclosed. Actually, some
Yeah, but it doesn't become, in terms of inference on an individual, that will not start becoming relevant until you've either got very small number of individuals in the first place, or you start getting so many SNPs in your model that you'll start effectively fitting a thing that's getting close to saturation. Now, under those circumstances, it clearly does. But for example, one of the things we've actually specifically got in here is we've got a disclosure control that looks at how many parameters there are in a model, and if it's above a certain proportion of the sample size in any study, it will block that generalized linear model. None of this will get around the Homer et al. Situation, because no matter what you do with, you can, if you produce these SNP-based estimates, you can do it. However, in fact, the fact that Homer et al. Exists as a problem has recently been overturned. So in America, they're now saying, no, we're not going to use that as a reason for not making data available at that level. So that's a contentious issue anyway. And remember, this is not being set up specifically for doing genome-wide association studies. I mean, yeah. Okay. Yes, exactly.
Continue this fascinating discussion, which brings up various things from the workshop over tea. So, break for tea now. I'd like to start up again at 3:30, so sorry for compressing your tea a little bit, but let's thank Paul once again.